Alright, hello and good morning to everyone. Today we're going to be talking about Michael Faraday. It's probably evening, actually. So, Michael Faraday. Some personal information about Michael Faraday. He was born on the 22nd of September in 1791 in London. He then died on the 25th of August in 1867. He started learning about science at the age of 14, and I'll speak more about that on the next slide. And he's responsible for numerous advances in electromagnetism, as we've been learning about for the past few weeks. So how he got his start. He was an apprentice at a bookbinder at the age of 14, where he decided that he was going to read all he could about science, and he'd pick up every book, and he'd teach himself everything that he possibly could. He then attended a set of 3 lectures performed by Humphrey Davy, who was a very popular chemist at the time. He then applied for apprenticeship with Humphrey Davy and was actually denied. So his biggest discovery was the homopolar electric motor, made in 1822. He based his work on Hans Christian Ørsted and André Marie Ampère's work, and you can recognize that some of these names, for example, Ampère, are very widely renowned names. And he basically took their principles and combined them to make the motor. So I'll speak. You'll see a bit more about that later on. But current through a wire creates a cylindrical magnetic field along the wire, as we've learned. So how it works: part of the glass vessel was filled with mercury. A magnet was placed under the vessel, and the stiff wires were connected to a battery. The magnetic fields of the wire and magnet interfered, and the wire began to spin. And I'll actually be showing you a video of this in a moment.
Here's how it works. The battery makes electrons flow through the circuit. In the glass, the electrons move from the copper wire that's hanging down and free to move through the salty water to the aluminum foil. That causes electrons to flow along the wire. You can use the right-hand rule to figure out what happens next. Point your thumb in the opposite direction that the electrons are moving, downward in this case. Point your index finger, also called your pointing finger, in the direction of the magnetic field as shown, and make your middle finger stick out at right angles to both of those. The middle finger indicates the direction of the force that the wire will experience. As you see, this is just the direction the wire is moving when on the right, as shown in the diagram. It moves outward from the diagram towards you. As an exercise, use the right-hand rule this way to confirm that the force will always cause the wire to rotate around the magnet. Note that we're talking about what happens to the wire in the magnetic field near the top of the magnet. Lower down, the wire is largely parallel to the magnetic field, and in that case there's little or no force experienced. The force happens when the direction of electron flow is at right angles or perpendicular to the magnetic field.
So here we can see an example of Faraday's electric motor that I've made here. You can see we have a 9-volt battery hooked up to the circuit in the diagram that I showed you. So we go from this end here, around up here. It's connected to this copper wire. And this copper wire, I have sanded off the edge so that the paper clip and the copper wire connect and conduct. And the paper clip is connected to another copper wire that's dangling around these magnets that you can see in the very center of the glass. Alright, and then the liquid that's filling the glass right now is salt water, so it's conductive. And then going up out of the side is some aluminum foil that I've folded and just tucked into the salt water so it isn't making contact. And then it is connected to the other side of the battery over here. And if you want to see it spin, you just got to agitate it a little bit, and you poke the wire, and it should spin. There we go. So, I thought that was pretty cool. Yeah, then just for reference as to why the one that I created didn't exactly wasn't spinning at the beginning of the video, is because I didn't interfere with it and make it start spinning. So all you have to do is poke it a little bit. Also, mine in retrospect could have had a bit more of a bend away from the magnet. It was more vertical, right up and down next to the magnet than it should have been. And this leads into the point of how most of the force comes from the top end of the copper wire, because it is closer to a right angle interference, which would have the most force propelling the wire around, where mine was not exactly at the correct angle for that. Anyways, it still worked. And this is just a quick explanation of what we just explained in the video. Some repercussions of the invention. So first step was to create electric motors. So you took that electric motor that you saw in the video, and that doesn't look like it could be generating much mechanical energy to do really anything. It was pretty flimsy, right? You'd have to scale up huge amounts of, you'd have to scale it up really, really big to actually get anything done. So we had to develop it a little bit more. Homopolar motors are now used in high torque wind turbines, as you can see in the photo here. And homopolar motors require less maintenance, so that's why they use them in the wind turbines, because, well, you can imagine doing maintenance on a turbine that is 60, 80, 100 meters high, whatever it is hard, right? It's also used for electroplating, which is something that someone else talked about, where you plate one object with a certain material using electricity. The invention paved the way for future improvements in the motor, which is what ended up leading us to the ability to use it in turbines. We now use electric motors for pretty much everything. You can see them all over the place, all robotics, electronics, cars even, and energy generation devices. It also increases the amount of pollution in the environment. That's just because this is talking about the old one with the mercury in it, because the mercury was actually toxic, as many of you know, and so putting mercury into certain sections of the environment that it wouldn't have occurred in naturally. For example, if the mercury used in the motors was just sort of, like, imagine these motors were mass produced at the time that Faraday had made them, which I know they wouldn't have been, but the way that all of the mercury would have been handled would have been terrible for the environment and people. Alright, so the progress of the electric motor over the years. So since Faraday's invention of the weak electric motor, there were a number of iterations of similar yet also similar motors that also had very weak mechanical power outputs. However, in 1834, Moritz von Jacobi created a motor with steady mechanical output that far beat anyone else in the field. 4 years later, he made a better one that could drive a boat of 14 people across a very wide river, and the one in 1834, by the way, actually set a world record, and it was only beaten 4 years later by himself. It took another year or two for everyone to catch up in around 1839 and 1840, and that's when larger companies started creating motors that either equaled or eventually surpassed Jacobi's own inventions. So how culture helped. Faraday had a drive instilled in his youth for knowledge. After apprenticing with the bookbinder, he was apprenticing with the bookbinder, he was self-taught and read as many books as he could, as I said, and that really showed a lot of discipline. He then attended chemistry lectures in his free time. I don't know how many of you would do that, but he did, and Faraday's also, this just accumulates to make Faraday a self-made genius who has determination and drive, much like many of the entrepreneurs that we see in today's society. His youth gave him the qualities he needed to persevere and succeed with his ambitions and plans, even after he got denied his apprenticeship with Humphrey Davy. We're excited. Thank you very much for listening, and have a nice day.